Let's turn our attention now to some other definition issues. What do we mean by, for example, a crude rate? Well, that's easy. A crude rate is when we take the numbers as they exist in the population, jam the numerator and denominator together, and get our answer. Crude rates don't have any refinement, any adjustment to them. They're just taking the numbers as they exist to construct our ratio. Crude in this context doesn't mean crude as in bad language. It means crude as in crude oil, unrefined, without anything being done to it. If I talk about how many people died in the United States last year, that's a crude mortality rate. Specific rate is something different. A specific rate, remember it as a subgroup rate, focusing on a section of the population, not the population as a whole. Usually we make these subsections of the population by cleaving the population along demographic lines. So if I talk about just how many men died in the United States last year, that would be a gender-specific mortality rate. If I talk about how many people died in the age range of 65 to 75, that would be an age-specific mortality rate. Looking at specific rates is important because learning that disease is more common in certain sections of the population, less common in other sections of the populations, helps us, one, target our health care and our prevention to those sections of the population, but two, also gives us some information that helps us understand what promulgates the disease or makes the disease more likely to occur. Both of these, crude rate and specific rate, are different than a standardized or adjusted rate. A standardized or adjusted rate is used when we're trying to do comparisons between two or more different populations. It is a rate for comparison, not for representation, but again, for comparison between two populations. The trouble is, as we're trying to compare two populations, we often find these two populations are demographically different, and that different demographics gets in the way of us comparing the health or disease issues which we want to focus on. What we end up doing with the standardized or adjusted rate is removing out the demographic impurities, the demographic differences, so we can get a clean comparison focusing just on the health issues we want to focus on. I know that's kind of abstract, so let me try to lay this out concretely. Here we have a set of stairs. On these stairs we have standing two individuals. You can tell I'm a gifted artist, of course, can't you? I want to make sure you understand who I'm talking about, so let's give these two people standing on the stairs some names. Let's call this first person Hillary. That's a pretty name, don't you think? I've always liked that name. Let's call this person Monica. That's a pretty name, too. So here we have Hillary and Monica standing on the stairs. And a simple question for you. Who's taller? Who's taller? Well, it's hard to answer that question, right? Because the stair is in the way here. The stair has Hillary elevated above Monica, so it's really hard to make a direct comparison of height. If we wanted to get a clean direct comparison, it should be obvious how we do that. We get Hillary to step down, be on the same step as Monica, Monica to step up, be on the same step as Hillary, or they both go some third neutral step. But as long as they're on the same step, we can do a simple, easy comparison. This is what we're doing with a standardized or adjusted rate. Simply getting the same level demographically, and because of that, therefore, we can get a simple comparison, not in terms of height, but in terms of health issues. That's the metaphor I want you to hold on to. Let me try a concrete example with you. Congratulate me. I've just been given a tremendous sum of money by the federal government to compare the rate of heart disease in two great American cities, San Francisco, California, and Phoenix, Arizona. I take that money and I hire my staff and I send them out across both of these cities, and with great effort, they find every single case of heart disease. They bring that data back to me. I put the data in the computer, crunch the numbers, and I discover, and lo and behold, after my analysis, there is 6 times the rate of heart disease in Phoenix than there is in San Francisco. True fact. 6 times the rate of heart disease. I now write up my data for an article in New England Journal of Medicine saying there's something about being in Phoenix that makes you more likely to have heart disease than San Francisco, right? Wrong. Now, this all hinges on what you know about Phoenix and what you know about San Francisco. So, for those that don't know, let me clue you in on some details that are important here. Phoenix is a lovely city. Desert basin surrounded by mountains. It's a beautiful, pristine environment and the kind of place that many people like to go to retire. When you drive around Phoenix, you notice quickly they're very old in Phoenix. I think the median age there is something like 74. They're really old in Phoenix. San Francisco, by contrast, beautiful city. 7 hills surrounding the bays, beautiful vistas. But it's not because of the weather, perhaps, the kind of place people go to retire. People don't go to retire in San Francisco, yet a lot of people move to San Francisco. Let's just say for other reasons and let it go at that. Suffice it to say, if anything, people in San Francisco tend to be younger than average. Well, you see my problem? When I'm comparing Phoenix to San Francisco, I'm not comparing apples to oranges, but I am comparing really old apples to really young apples. Hence my problem. What I need to do is get Phoenix and San Francisco on the same demographic step. Now, you're in luck, because the mechanics of how we do that is not tested on the step 2 CK. So how we do that is not tested. When we do that, what it means when we do that, and the implications of doing that, that is what's tested. So what we need to do is get a number so we have what would be true if Phoenix were like San Francisco, or San Francisco were like Phoenix, or they were both like some third standard population. In short, they must have the same demographics to have the same disease comparison be allowed. Now, notice what's happening here. When I say get them to have the same demographics, what I'm doing is making up what we call as-if numbers. Because Phoenix doesn't have the same population demographics as San Francisco. San Francisco doesn't have the same population demographics as Phoenix, but we're going to see what would the disease rates be if they, in fact, had the same demographics. What I can do is get them on the same step, and once I do that, I can then look more easily at the differences in rates of disease. So, when I do the so-called age-adjusted rate, what I find is now Phoenix has merely twice the rate of heart disease as San Francisco. Before it was 6 times. Once I've done the adjustment, now it's merely twice the rate of San Francisco. Notice what's happened. You can see that a large proportion of what looked like the huge difference is not due to any real difference. It's simply due to the fact there's more old people in Phoenix. You also should understand from that why it's essential that we do these standardized or adjusted rates, because it keeps you from making stupid decisions, keeps you from making bad interpretations. Under the non-adjusted data, you might say to someone, don't move to Phoenix, everyone dies of heart disease there, when in fact it's not heart disease really, it's about the age issue. Now, when do we do standardized or adjusted rates? Well, we do them in the following circumstances. 1, we do them when there's a difference in the populations in terms of some disease rate. And 2, at the same time, there's difference in some demographic variable. And 3, the disease is related to the demographic variable. And 4, when we do the adjustment, it matters. That is, doing the adjustment changes our impression and gives us a, we hope, better vision of what's happening in terms of the health status. We do this whenever we're trying to compare two populations that are demographically different, and we think that's getting in the way of us seeing clearly what's happening with the rates of disease. Now, we can adjust for anything. I've been talking about age because it's a common adjustment, but we can adjust for gender, ethnicity, education, socioeconomic status, income level. You can adjust for any variable that you can identify. Consider the following and tell me, in each of these cases, should I use age-adjusted data or should I use crude data? I want to compare the rates of heart disease in whites versus African Americans in the United States. Heart disease in whites versus African Americans. Should I use crude data or age-adjusted data? Well, the answer, of course, is age-adjusted data, because whites on average live 8 to 10 years longer than African Americans. If I don't do age adjustment, I'm comparing older people to younger people, and that simply doesn't give me a clean, understandable comparison. Suppose I want to compare rates of certain kinds of cancer in men versus women in the United States. Should I use crude data or age-adjusted data? Well, the answer there, of course, is again age-adjusted data, because women live on average 6 to 7 years longer than men. If I'm using crude data, I'm not taking into account that these are older people and these are younger people. I would get a distorted impression. Suppose I want to compare rates of blindness in the United States versus the country of Haiti in the Caribbean. Blindness in the United States versus Haiti. Should I use age-adjusted data or crude data? Well, again, I should use age-adjusted data. Why? Because people in the United States live 20 to 25 years longer than people live in Haiti. And since we know age is related to blindness, the age adjustment is essential to make sure we're comparing like to like, not older to younger. Are you getting the message from these examples? When do we want to use age-adjusted data versus crude data? Well, we always want to use age-adjusted data, because the odds of finding two populations that are the same ages are, on a probability basis, very small. What we need to do is get them on the same step. The adjustment is what does that, gets things on the same particular step. Now, what does it mean when I do this adjustment? Well, if I find two populations that are different in some disease and different in some demographic variable, if I adjust for the demographic variable and then the disease difference disappears, simple logic tells me the original disease difference I saw was actually due to the demographics I adjusted for. Let's do that again. If I find two populations different on disease rates and different demographically, if I adjust for the demographics and the disease difference disappears, it tells me that the original difference wasn't due to the disease rate, it was due to the demographics. Let's try a commonly used example. You all know that physicians have a higher suicide rate than the general population, right? Everybody knows that. Physicians have a higher suicide rate. The question, of course, is why? Why are physicians more likely to kill themselves? Well, commonly cited reasons are it's a stressful job. There's a lot of responsibility, life and death decision making, and then there's that special access and use of pharmacology. All these have been postulated as reasons why physicians have higher suicide rates, and none of them are correct. Why do physicians have higher suicide rates? Easy, because they participate in higher socioeconomic status. Now follow the logic here. Physicians have higher suicide rates than the general population. Fact one. People that are high SES have higher suicide rates than people that are low SES. Fact two. Physicians tend to be of high socioeconomic status. Fact three. So the question before us is a simple one. Are physicians killing themselves because of some quality intrinsic to being a physician, or merely because they participate in higher socioeconomic status? How will we answer that question? It should be obvious by now. We're going to get an SES-adjusted suicide rate for physicians. And when we do that, what we find is the suicide rate of physicians is dead on even to the general population, telling us the entire elevated suicide rate is not due to stress, responsibility, drugs. It's due to participation in socioeconomic status. Once again, from the illustration, you see why it's essential to do these kind of adjusted or standardized rates. It helps us from reaching conclusions that look good, make sense, but in fact are wrong. Standardized or adjusted rates lets us ask the question, if this weren't in the way, then what would things look like? And therefore help us get a better, clearer sense about what reality looks like. So, with that concept now, I hope fairly well understood, let's talk about how you might have to use this on an exam question. Let's try to build a question for you. Once again, you see a large data table in front of you. Now, I know this looks intimidating, but as before, walk through it with me, and you're going to find this is actually a much more basic question than you might first assume. The question begins by pointing out to you that, well, the disease rate in population A, you can see is higher than the disease rate in population C, 2.3 per thousand versus 1.5 per 1.6 per thousand. The question, of course, is why? Why is there a higher rate of disease in population A than there is in population C? Now, you may see all kinds of options presented to you, such as option C has better health insurance. Population C has better ambulance transport for the elderly. Population C has better physician-to-population ratio. Population C has a better social and physical environment. All those, although they sound good, when you look at the data, cannot be the reason. See, when you look at the data, you can see over here on the left that the disease rate rises with age. As we go from younger to older, we go from 1 per thousand to 3 per thousand. You can further see that in population A, we have half of the population, 3,000 out of 6,000, in the older group. You can also see that in population C, we have half the population, 3,000 out of 6,000, in the younger group. Well, of course there's more disease in population A. Not that population A is, quote, sicker. Population A is older. If we did a certain kind of adjustment, and again I won't trouble you with the mechanics of this, you would find that both population A and population C look like population B. In other words, they would both have the exact same rate of disease. Once we adjust for age, the difference between the two populations simply disappears.